It's summer, a time for relaxation, some fun at the beach, and intense quantum mechanics. What? Don't look at me like that. Today I'm turning to my trusty beach balls to help explain one of the weirdest ideas in quantum mechanics, neutrino oscillation. Put on some sunscreen and get ready. This is EvenBananas. A quick refresher on neutrino oscillation. This odd behaviour is all about how neutrinos appear to change as they travel. So, an electron neutrino produced in the Sun can arrive in a detector on Earth as a muon neutrino. If that neutrino doesn't interact in the detector and travels further, it can change into a tau neutrino. We've used this animation before to represent oscillation. It might even be how you imagine it happening at a particle level. The problem is that it's not quite right. I like to think of it in a different way. Imagine you have an incredibly stylish pair of sunglasses that let you see only a sliver of the world. And someone passes you a ball. This ball is red. You throw the ball to a friend who's also wearing a pair of the special glasses. No, this ball is blue. Wait, what? You and your friend would be pretty surprised until you realised you were looking at a beach ball with 3 different colours on it. This is similar to what happens with neutrinos. Imagine each colour on the beach ball represents a different flavour: electron, muon, and tau neutrino. Neutrinos actually travel as a mixture of these 3 different flavours. And catching the beach ball is like when a neutrino interacts in our detector, producing its partner particle, or in this case, appearing like one single colour. In general, if a muon is produced in a detector, we say, well, that must have been a muon neutrino. If we see an electron, we infer an electron neutrino. And if we see a tau, it was a tau neutrino. So our original animation doesn't quite work. The neutrinos aren't literally changing into different particles, they're travelling as this weird quantum mix of all 3. But our vision is limited and we can only see them when they interact, producing one particular flavour. Side note, I admit my beach ball analogy isn't perfect either. When a neutrino interacts, it fully commits to that one flavour. So a better analogy would be if the beach ball turned into a solid colour when I caught it. If you have this advanced beach ball technology, please contact me. One place the beach ball analogy works great though is with this idea of probability. You never know what colour you'll land on or what neutrino flavour you'll get. But if the red section of your ball is really big, then you have a greater chance of seeing red. And here's the thing, we can have beach balls with different sized stripes. You can imagine all sorts of different combinations, but there are 3 mixtures that we're particularly interested in. We call these the mass states of the neutrino, and there are 3 of them. Mass state 1, mass state 2, and mass state a million. Just kidding, it's mass state 3. We're so good at naming things. This beach ball here is actually the right quantum mixture for mass state 2. There's a 1/3 chance of seeing each flavour, muon, electron and tau, when it interacts. A very evenly balanced neutrino. My personal favourite. A mass state 1 neutrino shows up 2/3 of the time as an electron neutrino and 1/6 of the time as the other flavours. A mass state 3 neutrino, on the other hand, almost never shows up as an electron neutrino. So now we know that there are 2 totally valid ways to think about neutrinos: as flavour states, which is how we normally see them interact, and as mass states, which is how they like to travel. As you might have guessed from the name, the mass states also have mass. Here's the mind-melting part. These flavour states and mass states don't line up. So neutrino flavours, which is how we typically end up talking about neutrinos, don't actually have a well-defined mass. Asking what is the mass of an electron neutrino is like asking, is a banana left-handed? It's a property they just don't have. Only certain quantum mixtures have definite masses. Those are our mass states. Quantum mechanics is weird, and it does not care how counterintuitive this seems. It's a really hard concept to wrap your head around. Each mass state can produce different flavours, the same way the beach ball is a mixture of 3 colours. And each flavour is also a mixture of the mass states. After all, if I think I'm holding a red ball, I could still be looking at any of the 3 beach balls. I often get asked, if neutrinos are turning from one flavour into another, doesn't that mean they're changing mass? Hopefully the beach ball analogy helps explain that they aren't. The neutrino itself isn't changing, but the probability of seeing a particular flavour is. It turns out that different masses were inside them all along. And so were the flavours. Okay, we've gone into a lot of detail about the flavour and the mass states, and I want to bring it all back home to oscillation. We know that, depending on a neutrino's energy and how far it's travelled, we're more likely to detect certain flavours of neutrino. So, what's the deal? Well, now you know that neutrinos are travelling as a mixture of mass states. And because they have different masses, they're all travelling at very slightly different speeds. The differences are so small that we actually can't measure them. But it does mean that the quantum mixture changes as a neutrino travels. Essentially, the stripes on our beach ball are growing and shrinking over time, and that is what gives us the pattern that we see in oscillation. When the mix changes, the chance of catching one of our quantum beach balls changes, so the probability of seeing a particular flavour changes. So all the quantum weirdness boils down to this. The probability of detecting any given neutrino as any given flavour goes up and down as the neutrino travels. That's why we call it oscillation. And that's how we end up with detectors at different distances seeing different neutrino flavours. Scientists designing experiments to study oscillation can work backwards to figure out the best location for their neutrino detectors. That is, the spot where they'll see the most neutrinos changing flavour. Once you know how much energy you'll have in your neutrino beam, you can figure out how long you want it to travel for. A bit of maths, and you can basically draw a circle around the starting point with the right distance. Find a mine to shield your experiment from cosmic rays, and you're ready for some neutrino physics. If these concepts are a lot to take in, you are not alone. A common saying among physicists is, if you think you understand quantum mechanics, you don't. Do you have a different analogy for thinking about neutrinos? Do you hate beach balls now? We love to hear from you, so let us know in the comments. A mass state 3 neutrino, on the other hand, almost never shows up as an electron neutrino. Thought it would go further behind me than it